Quantum states in flux. What happens when a system never really transitions? Stay tuned to unravel this intriguing physics dilemma. And here we are right in the middle of time-dependent perturbation theory, starting again with 11.3. And to which we want to solve equation 11.17, which are the equations for time-dependent perturbation theory, for the case of a time-independent perturbation. Okay, so now we're trying to mix and match and see what happens. Now, this is assuming that we're in the initial state CA, because the coefficient's 1, and the initial state CB is 0. So we're only all in CA. And we want to check that CAT squared plus CB squared and the magnitudes equal 1, conservation of probability. And the comment for this question is, ostensibly, the system oscillates between pure state A and some state B. Doesn't this contradict my general assertion that no transitions occur for time-independent perturbations? No, but the reason is rather subtle. In this case, psi A and psi B are not and never were eigenstates of the Hamiltonian. Okay, that's going to play a big part here soon. A measurement of the energy never yields EA or EB. In time-dependent perturbation theory, we typically contemplate turning on the perturbation for a while and turning it off again. Hence, time is the perturbation effect, not some rearrangement of the potential. And here, in order to examine the system, at the beginning and at the end, psi A and psi B are eigenstates of the exact Hamiltonian. And only in this context does it make sense to say that the system underwent a transition from one to the other. For the present problem, then, assume that the perturbation was turned on at time t and turned off again at time big T. This doesn't affect the calculations, but it allows for a more sensible interpretation of the results. Okay, so why do we care? Because in this chapter, we're dealing a lot with transitions. In particular, we're going to get to the forbidden states here soon. So be prepared to deal with all of those identities again. And then this challenge really comes in how do we interpret the results of time-dependent perturbation theory? Again, assuming that the perturbation is the time dependency part. That being said, there's a lot of work in this video, so if you want the PDF for your collection, feel free to comment and I'll send you the link, or you can just go straight to the Patreon page. Pretty easy to access it there. So we had a big question here, so we'll just jump right in. But if you're curious about the world of science, be sure to subscribe. I post educational content every week to quench your thirst for curiosity. And now let's dive into the heart of Chapter 11. All right, starting with stop number 1. So since the equations listed in 11.17 are coupled, meaning that the first derivative of CB ties in with CA, which is what we see here. CB dot equals CA. So these things are coupled. And in order to get them uncoupled, we have to go ahead and take the derivative of it, and that derivative will allow a substitution later. So here, if we take the time derivative of C dot B, and then we just see that we plug in the equation from 17, we see that we really have a product rule here with the exponential and the CA term. So take the derivative of the first thing, leave the second thing alone, followed by the derivative of the second thing, leave the first thing alone. Not too bad there. But now what we see here is that we can distribute all of this stuff into the product rule, and then upon doing so, we see that we recollect terms. So I have this negative IH bar, HBA prime, e to the I omega naught t CA. All that green stuff is exactly the same CB equation that we started with. Notice what's in the bracket, notice what's highlighted in green. Cool, we recover the CB equation. But now that we have a C dot A, this is also the other coupled equation that we could substitute in below. And now that we have these substituted in, we now have a differential equation, although via second order, that we can go ahead and solve. So we really have to start by cleaning this up, and we see we got a lot of moving parts in doing so. Alright, so from there, we substituted in the CB, so we only have an I omega there, not too bad. We have an I squared, H bar squared after the negatives cancel. And then what we do is we rearrange this matrix element HAB And we did so by putting a star up there. Again, that was one of the common things we saw back in chapter 6. Switch the indices at the cost of a complex conjugate. No big deal there. That allows us to write it as a magnitude down here. And then we see that upon doing so further cleanup, we see that the e to the I omega t minus I omega t, those cancel, so that'll simplify to 1. Easy enough, leaving us just with another CB term. So here's what we have all simplified down. Recollecting everything, we see that the matrix elements are defined in 1 or 11, 13. So all good to go there, but it's the same thing we had dealt with back in chapter 6, so not too bad to deal with. But what we notice here is that this is a second order derivative, okay? In particular, it takes the form of a second order homogeneous linear differential equation with constant coefficients once we put it in standard form. And we see that we have c double dot minus I omega naught c dot, and then plus another constant, cb. So putting that with substitutions, we see that with this differential equation form, it can be solved using an auxiliary equation. Okay, and all we have to do is determine what type of roots it has. Hence, we need the auxiliary equation, m squared minus a, well, that should be m. I don't know why I used x. Let me change that real quick. It should be m. Differential equations books, they use different notations, so whatever your book used, go ahead and use. But here, nonetheless, what we see is that it's our coefficients, where the second derivative gets a square, first derivative gets just a single variable, and then the last doesn't get any. So we go ahead and solve this using the quadratic equation, and then from these solutions, we can determine what form to use. So go ahead, chug it out. We see our substitutions coming in, easy enough. Now we're going to simplify this down. We get that negative outside, it turns to an I there. And then all this red stuff we'll just label as omega, make our life a lot simpler. And then from there we see that we can factor out an I, just as we would expect. And then we have, I over 2 omega naught plus or minus omega. And from this, what we can tell is that, well, clearly with the plus or minus, we don't have repeated roots. So we have two distinct roots. And if we have two distinct roots, we take this form here. Okay, so that's y equals c1 e to the m1x plus c2 m2x. Again, I just copied this form from a differential equations book I had. Clearly, the variable here is with respect to time, so we need to put that in. So cb is a function of time. That x goes to time. Our roots here come from this, so plus sign on this side, minus sign on that side. And now, since we're in the exponential, I did all the algebra in the PDF, but we get the gist of it here. Color coding it, we can split them up. And the reason we split them up is because there is an I omega naught t over 2 in both of these terms. Let's go ahead, factor them out. And then we'll go ahead and clean up very quickly so we can apply the initial conditions given to us. Okay, so once we go ahead and factor that out, clean it up, we go ahead and put in Euler's identity. So this green exponential goes to cosine plus I sine. The blue goes to cosine minus I sine. And now we can distribute and clean up and just get two new coefficients for the cosines and sines. All right, so distributing the coefficients, C1, C1, C2, C2, recollecting terms here. All my terms on cosine go to green, all my terms on sine go to blue, and we see that we get a compact equation for CB, where we have A and B as just random constants, so it doesn't matter. That's the beautiful part about it. And in fact, I think we showed either in this class or in the E&M book how exponentials and cosines lead to the same result, or exponentials and trigs lead to the same result. One's a traveling wave, one's a standing wave, so they have different interpretations, but nonetheless, we've seen this before. So with that, we also know that the omega substitution we used was omega naught squared plus 4 beta squared, which we just put in all of this, the magnitude squared here and h bar squared there. So we have all our substitutions. But we still have to apply the initial conditions and solve for A and B. Okay, so the initial condition given to us was that at t equals 0, the CB coefficient equals 0. Okay, so I color code them differently so we could see the results. But applying this, we see that if t equals 0 in red, the 0 is going to cancel out a lot of things here, so that's going to be helpful to us. That being said, before we continue, If you're finding this helpful, don't forget to give it a thumbs up. It helps more curious minds like you discover this content. So with that, let's clean up this initial condition problem. Alright, so now we're left with the exponential, and it has a 0 in its argument, cosine has a 0, and sine has a 0. We know that the exponential goes to 1, cosine goes to 1, and the sine goes to 0. Cleans up quite a bit. So we're left with a plus b, or a plus 0, which is just a, but the whole thing was said to be 0. So we know that a equals 0. With that, we confine ourselves to CB. C lowercase b of t is equal to some function b with the exponential and the sine. Okay, but we were still given another initial condition, mainly that CA of 0 equaled 1. But in order to use this, we have to take the derivative of our CB function in order to substitute in the CA term and solve for CA, and then upon solving that, we get the B coefficient. So a lot of work left to do because, again, these were coupled equations. So let's go ahead and solve for CB by taking a derivative and then go ahead and applying the CA. So here, derivative, both sides, easy enough. So what we have here then, again, a product rule inside, so B can come outside. Derivative of the first, leave the second alone. Leave the first alone, derivative of the second. We can clean this up. What we want to do again here is notice that our exponential terms are the same, and omega over 2 can be factored out, but we have to put the omega term in here. And again, we kind of want to do this because in certain regimes, omega versus omega naught, their ratio tells us a lot about what to keep. So getting used to seeing omegas over each other is very helpful. But nonetheless, what we see here is that the time derivative of CB is equal to omega over 2 b e to the I omega naught t over 2. Factored all that out. So we're left with a cosine, excuse me, a cosine and an I omega naught over omega sine here. But because we also know that CB dot is equal to negative I over h bar with the matrix element and a positive exponential in CA due to equation 1.17, we can set these two things equal to one another and solve for the CA term and ultimately get that B term. All right, so applying, or rather solving for CA of t, we just had to divide everything that was on it. Okay, so now, again, more cleanup duty, cleaning up these exponentials and matrix elements, and of course that nasty imaginary number. So we see that we get I, h bar. It's red here because we cancel out this negative by multiplying by the conjugates. The matrix element stays under, and we have omega over 2. And now we see that we just modify this, a positive I omega t over 2, into a negative 1 because we minus a whole factor of I omega t. Easy enough, just keep the algebra the same. And then we see that we have B with our cosine and sine, as expected. So now what we can do is apply the second initial condition where at t equals 0, 0 being in red for t, we know that the whole thing equaled 1. So from here, plugging in 0, we see everything to go. This turns our arguments to 0, 0, 0. And now we can clean up pretty much everything. The e goes to 1, cosine goes to 1, and the sine goes to 0, getting rid of that whole thing. So ultimately in the cleanup, we see that I h bar omega over 2 h prime with BA for the matrix element times B is equal to 1. With that, we quickly see that B is equal to I h bar omega over 2h, or the reciprocal, whatever you'd like. And now we can go and back solve all of these and simplify them. So let's simplify the CA equation since we're already here, and then we'll plug this into the CB equation. So plugging in our coefficient here, we see that all of this stuff and all of that stuff cancel out very quickly, very wonderfully. We love to see that. So CA in general then is e to the minus I omega naught t over 2, the cosine term, the I sine term, easy enough. But now that we remember that we had B, E, and sine for the CB term, the B coefficient that we just solved for, B coefficient that we just solved for, is the 2h prime BA over I omega naught, or omega with h bar. These are pretty gross looking things together, so be very well aware with our omega substitution. Okay, so let's take a quick look at these things too. This one has a negative, this one has a positive. This one's all complex. This one's all real for the signs. We still have complex here though. So eventually, whenever we find the magnitudes and stuff, we should have a lot of cancellations. So just be aware. Okay. And then here, that brings us to our conclusion of finding CA and CB. Okay, that was quite a journey, and differential equations had quite a throwback. But now that we're done finding them, we still need to check that CA of t squared plus CB of t squared equals 1. Okay, and what this tells us is that we're going to have some kind of oscillatory behavior, clearly sine and cosine and the exponentials, between the two states. And we remember that this whole system works because when we solved for the time dependent or the time independent part of the Schrodinger equation, we were able to put the time dependence back in chapter 2 with the exponential that had an energy and time factor. That's this exponential here. Omega naught was the difference of energy states over h bar. Okay, so we're trying to use these coefficients and tell you that because of the change in energy, the coefficients modified themselves, and that's what we have in the time dependent part. But again, we should still have a normalization condition that holds because we want conservation of probability. So let's double check this statement here and we'll be good to go. So starting with CA of t squared, we see that that means that I need the conjugate multiplied by the thing itself. And so applying the conjugate, that I goes to positive, that one goes to negative, is highlighted by red. And we still have to clean this up here. So we see that exponential, they come together. They're conjugate pairs, so the arguments cancel to 0. So e to the 0 will be evaluated later. Then we see that negative I and positive I, once we distribute the cosine and sines, those cross terms cancel. Oh, what a thing of beauty. And then we're left here with, okay, well now I have e to the 0, and then I have cosine squared plus my omega squared plus my sine squared. And that's all that we're left with because e to the 0 is 1. Okay, so now I think you can see the setup for what's going to happen come when we add them together with Pythagorean identities, things like that. It's going to be very nice. All right, so here then, what we have is CB squared, again, the thing with the conjugate times the thing itself. Let's notice that the matrix element, we can switch the pairing here with the conjugate here, so we can switch BA to AB at the cost of a conjugate. But also this I down here puts a negative there. Our exponential goes negative, easy enough. All of this, we just need to multiply together. As a result, what we have here is more distribution and cleanup on its way. Okay, so now what we do here is, and upon applying it, we see that H prime AB is now matched with H prime BA, but we'll go ahead and simplify this one to turn everything into ABs. We have I squared here, that cancels with our negative here. Once again, the arguments of the exponentials cancel, and we're left with a sine squared. Easy enough. Now, this is kind of foreshadowing in all of this, where we're trying to put this in terms of AB so that we can have a modulo square on it. But that's going to come into a substitution here later. And trust me, it will help you quite a bit. So keep this in mind when you're substituting. There's always another game plan for when you add the two together. Noticing here that I have cosine squared added with our omega squared sine squareds, and then I have all of these coefficients from CB and sine squared. Notice that in purple I have some nice factoring that I can be done. So I take the omega out, I take the sine out, and I'm left with omega not here, and I'm left with 4h bar or h prime AB squared over h bar squared. That's all in here. But remember what we made our substitution variable when solving the differential equations. That's right, we made all of that omega squared. Okay, in particular, we made it into a square root, so we're fine there. So upon plugging in omega here, the omegas cancel, and it's almost like a thing of beauty how it sets itself up. So because of this, I'm now left with cosine squared plus sine squared of the same argument. Pythagorean theorem comes through again, and we get 1. So we just verified that CA squared plus CB squared equals 1. That is amazing, and we know we have conservation of probability. All things are good and well in the quantum world, so we're good to go. But that was quite a journey. And again, as the author tells us, that the perturbation being time in this theory, the equations for 17 was that the time dependency was the perturbation. So if my perturbation is now something that's time independent, my time on, time off posed in a question, that had nothing to do with the actual state of the Hamiltonian not being time dependent. So this has a lot to do with, and it'll come over and over again, and it's a lot to grapple with. So I would read this chapter over and over again because a lot of this chapter is going to be used in most of the research that we have. So keep that in mind, and you'll be good to go. All right. So that was a very fun journey. Brought us back to a lot of different routes, including differential equations, all their substitutions, all the cleanup, lots and lots of algebra as always. So share this with a friend who's also curious about science, and let's grow this community together. The community has been very rewarding if you give into it. They help out in many ways. Supporting this channel is, one of the biggest things that I am thankful for, but also the feedback, the messages, the kind of ideas and concepts that are being proposed. I have a very big feeling that 2025 is going to be a very fun year of academic exploration, especially with the machine learning models coming out to help us visualize these things and not just talk in hieroglyphics. So definitely keep updated. I think I'm gonna make a new group chat either on Discord or we'll find some site that we can have a group chat. But there's gonna be a lot of things cooking up for 2025, so definitely stay tuned. As always, thank you for watching, and until next time, stay curious.